In this video, we discuss two topics: Sigmatropic rearrangement and Claisen rearrangement. Claisen rearrangement is a type of Sigmatropic rearrangements. So we discuss Sigmatropic rearrangement first, and then move to the Claisen rearrangement. Now, what is a Sigmatropic rearrangement? It's a pericyclic reaction involves the migration of a sigma bond. Second part of this, migration of sigma bond. That is very clear. One sigma bond moves from one atom to another atom. Now, what is this pericyclic reaction? Pericyclic reactions are reactions that moves through a cyclic transition state. So if the transition state found in a particular chemical reaction is cyclic in nature, then you can call it as a pericyclic reaction. So sigmatropic reaction is a pericyclic reaction involves the migration of the sigma bond. In one example, we will see this. There are different types of sigmatropic rearrangements like 1,3 sigmatropic rearrangement, then 1,5, 1,7, then 3,3. So we discussed a few of them. Consider the example CH3. So CH2 and H is taken here. Then CH double bond CH2. Here you can see a few unsaturated carbons and one saturated carbon, and saturated carbon is attached with one group. Here the group, it can be any group, so here we consider the group as hydrogen. So for explaining the sigmatropic rearrangement, we need to number this compound. So always put carbon number 1 to the saturated atom, saturated carbon here, then continue numbering 1, 2, 3. This one is a saturated or sp3 hybridized carbons, and other carbons are sp2 hybridized. On heating, the rearrangement takes place in such a way that the hydrogen atom or the group present on the first carbon will migrate to the third carbon, and a new bond will be formed between hydrogen and the third carbon. The resulting compound will be CH2 double bond CH CH3, or I can write it as CH2H. This is the newly formed sigma bond. Along with that, you must have noticed this double bond has shifted to the 1,2 carbon. Earlier, the double bond was present between carbon number 2 and 3. Now it is between 1 and 2, and the migration happens between 1 and 3 carbons. So it is known as a 1,3 sigmatropic rearrangement. Consider another example. CH3, so CH2H, then CH, double bond CH, single bond CH, and double bond CH2. Here too we have only one sp3 or saturated carbon, so put carbon number 1 to that saturated one, then carbon number 2, 3, 4, and 5. Here the last unsaturated carbon is the fifth carbon, so migration of this group from the first saturated carbon takes place to the fifth carbon. So the resulting compound after rearrangement will be CH2 double bond CH, single bond CH, double bond CH, CH2H or CH3. Here you see in the beginning 1,2 carbon is a single bond, but here it is 1,2 carbon a double bond, and 2,3 carbon a double bond here, but here 2,3 carbon a single bond, and 3,4 it was a single bond, now it is double bond, and then after that 4,5 now single bond. So alternate double bonds and single bonds are coming, or these double bonds are shifted like this. Here the migration took place between first carbon and fifth carbon. This type of rearrangements are known as 1,5 sigmatropic rearrangements. The sigma bond, a new sigma bond is formed on the fifth carbon. It was there on the first carbon, now it is there on the fifth carbon. So in both these examples, the migration is from sp3 carbons, saturated carbon, to unsaturated carbon. So in our example, both the carbons were sp2 or it can be sp2. So from saturated carbon to the unsaturated carbon. Consider Third example, consider a compound like this. There are two double bonds. It is hex 1,5-diene, right? Okay. Here you can see that there are two saturated carbon atoms in between. There is no conjugation there, complete conjugation of double bonds there. In between there are two sp3 carbons, and after sp3 carbon there is a conjugation, like a double bond is there, right? So as per, or like we did in the previous two examples, sp3 carbon should be given carbon number 1. So carbon number 1, carbon number 2 and 3 here, 1, 2, 3 here. So in this compound, this sigmatropic rearrangement takes place like this. This 1-1 bond will cleave, 1-1 bond will cleave, and a new bond will be formed on 3-3. The third carbon atom of the top one and the third carbon atom here on the bottom side, they will make a new bond. 1-1 will break and 3-3 will form. At the same time, double bond will shift their place. So that happens in both our previous examples too, right? The shifting of double bonds. So the resulting compound will be, so these are the 1, 2, 3 carbons, 1, 2, 3 carbons. Now a new bond is formed between the 3 carbons and the double bonds have shifted like this. There is a rearrangement. Here the new bond is formed between 3 carbons. So it is a 3-3 sigmatropic rearrangement. 3-3 sigmatropic rearrangement. So the same example, same type of rearrangement with another example. If I show it like this, consider a group is present here. A group X is present here. Now what happens? The same sigmatropic rearrangement. 1, 1, 1, 2, 3, 1, 2, 3. So 1, 1 will break, 3, 3 will form. So a 3-3 new bond is formed, double bonds have shifted, X, the group is there. So this rearrangement is actually known as COP rearrangement. About COP rearrangement and oxy-COP rearrangements and aza-COP rearrangements we discuss later. Now we will move to the Claisen rearrangement. Before that, see 1-1 bond breaks and then 3-3 bonds are formed. Keep that in your mind. Now Claisen rearrangement. Claisen rearrangement is explained with an aryl allyl ether. Aryl allyl ether means an ether that contains allyl group and aryl group, or with a vinyl allyl ether, an ether that contains allyl group on one side and vinyl group on another side. Here we explain Claisen rearrangement with an aryl alkyl ether. Consider an aryl alkyl ether, benzene ring with oxygen. Now we need an allyl group, so it is CH2, CH, double bond, CH2. Here, this carbon atom is an sp3 hybridized carbon, and oxygen also an sp3 hybridized. And after this sp3 hybridized carbon atom, that allyl carbon, there is a double bond. Then after the oxygen atom, which is sp3, there is a double bond on the benzene ring. So there is chance for 3-3 sigmatropic rearrangement. So consider carbon number 1, carbon number 2, and carbon number 3 here. So carbon number 3 is this thing, and oxygen we put number 1, then carbon number 2, and this carbon number 3. When the 3-3 sigmatropic rearrangement takes place, a new bond will be formed between these 3 carbons, and 1-1 bond cleaves, and the double bonds will shift from 2-3 to 1-2 positions. The compound formed will be ring with 2 double bonds and double bond oxygen. A new bond is with CH2, then single bond CH, double bond CH2. Okay, now this is not a benzene ring because only 2 double bonds are present. It has lost its aromaticity. Aromaticity gives higher stability to this compound. So to replace or regain that aromaticity, the hydrogen atom present on the ortho carbon will be removed as H plus, and then this double bond will shift towards oxygen. Oxygen becomes O minus, and H plus gets attached to it. So it's a tautomerization reaction. The resulting compound will be double bond is regained here in the benzene ring. So aromaticity is regained, or double bond O became OH there, then CH2, then CH, double bond CH2. So we got CH2 CH double bond CH2 group on the ortho position, and this step is a tautomerization reaction. Here the second step, the compound we got after the first step can undergo a different type of rearrangements other than tautomerization. Like here we consider this carbon atom. This carbon atom is an sp3 carbon, right? This carbon atom is an sp3 carbon, and this carbon, and both of them have double bond. So if I write carbon number 1 here, then it is 2, and here it is 3. And if I put carbon number 1, since it is sp3, then carbon number 2 and carbon number 3 here. Again, another rearrangement possible there, right? So 1 bond will break, and a new 3 bond, the third carbon of the benzene ring and the third carbon atom of this allyl group can make a bond. The resulting compound formed will be 6-member ring with 1 double bond here. Here double bond will shift to the 1 and 2 carbons. A new bond is formed between the third carbon and the third carbon of the allyl. So it is CH2, single bond CH, double bond CH2. How? This double bond will shift here, and then this double bond will shift here, and then new bond will be formed between these two, and a double bond oxygen here. And still this compound is not aromatic, and to regain the aromaticity, this hydrogen can get removed as H plus ion. This bond shift here, then this comes to minus, and the compound will be OH. Double bonds are now here, then OH here, then CH2, CH, double bond CH2. Now we have this allyl group on the para position, and the first reaction we got it on the ortho. So this is the first step. After the first step, two reactions are possible. Either it can undergo tautomerization, or it can undergo further rearrangement to form the para products. But mostly this ortho product is formed in major quantity, since the second rearrangement takes place less, as the tautomerization takes place faster. But consider this compound. Here, both the ortho positions are blocked by R groups or alkyl groups. Here, when the rearrangement takes place, this alkyl group, so 3, 3, so this one is 1, 2, 3, 1, 2, 3. So rearrangement takes place, and you will get double bonds here, here double bond oxygen, and then here one R group is there, and the newly attached CH2, CH, double bond CH2. Here we don't have any hydrogen atom to show the tautomerism. Hence, automatically it undergoes second rearrangement. 1, 2, 3, 1, 2, 3. So 1, 1, 1 cleaves, and this allyl group will migrate to the para position, and the resulting compound will be double bonds here, then double bond oxygen atom, and now the allyl group is here on the para position, CH2, CH, double bond CH2. So no tautomerization takes place after the first step. So complete rearrangement takes place and para product formed. After this, tautomerization takes place. Tautomerization takes place, you will get the resulting compound as OH, OH here, and then CH2 allyl group here, CH2, CH double bond, CH2. So you will get para product as the salt product or the major product when you block both the ortho positions of the benzene ring of the aryl allyl ether. Then Claisen rearrangement will result a para product. Otherwise, the major product formed will be this para allyl ortho allyl substituted phenol. Hope you understood the portions, both Sigmatropic rearrangements and a Claisen rearrangement. Thank you.